I joined the nuclear industry over 30 years ago in the NNC days, and since then there's been various transitions of the company, and eventually we've been bought out by Amec and part of their sort of power and process division. So today I'm going to give a very brief overview, though to the time limitation I apologise, it'll be a somewhat a brief superficial talk. I'm going to concentrate on the primary coolant chemistry of the three main reactors, the advanced gas-cooled reactors, the pressurised water reactor and the boiling water reactor. The boiling water reactor, of course, we don't have a boiling water reactor in the country yet, but there's one proposed at Wilver, on the Wilver site. There's all sorts of other interesting chemistries that go on in other systems. For example, in the boilers, the boiler water chemistry, all the ancillary circuits, and of course the other reactors, which I'm not going to mention today, are the Magnox. We still have one Magnox station operating. The fast breeder reactors, the alkali metal cooled reactors, and of course the high temperature reactors, the helium cooled reactors. So maybe it's more of materials interest there rather than chemistry. So we'll start off with the advanced gas-cooled reactors, AGR, CO2 cooled, operating at 40 bar. And the inlet temperature is about 340. These are typical values, incidentally. Each plant varies. They're all different, but typically they're 340 centigrade and 640 outlet. So there's quite a temperature differential. And the gas flow, we're looking at 4 tons of CO2 a second. It's graphite moderated, graphite being a convenient moderator for a gas-cooled reactor. It's about the lightest element you can find in the periodic table without giving you any trouble in the reactor. And the output, we're looking at, they're twin reactors, so we're looking at 2 times 660 megawatts. There's a schematic diagram here just to demonstrate the flow of gas, if you like, going the reentrant flow through the hot box stone, through the core, gas circulator at the bottom, and the boilers. There's only 2 shown there. They're spaced. There's 8 boilers around the AGR, and above the reactor compartment there's a large sort of refueling room, refueling hall, so that you can take the top off and drop the new fuel stringers in. This is a somewhat simplified version of the chemistry that's going on. I must point out that we've got a whole host of radiolytic reaction in a high radiation field, so we're producing a host of free radicals and excited species. I'm not going to go into all that detail, except to ask you to bear that in mind. And so this slide is really a representation of the main features that are going on. CO2 is at high temperature and pressure is an oxidizing agent. Under high radiation field, it'll dissociate into carbon dioxide and oxygen atoms, and the oxygen atoms will in fact react with the graphite moderator. The graphite moderator over the years has gradually been disappearing, mass loss, but this is quite acceptable. It's reviewed every year, and so far we're doing okay on graphite mass loss, but it forms carbon monoxide, and furthermore the CO2 could also react with the graphite directly to form carbon monoxide. Now, in order to mitigate the oxidation process from the oxygen atoms, we feed in methane, and methane is there as, if you like, a reducing agent to mop up any oxidizing species. And this sort of mechanism you might find is production of methyl radicals and OH radicals. And there's follow-on reactions of these producing other hydrocarbons, unsaturated, both saturated and unsaturated. And the reaction with OH, of course, and inevitably you're forming water vapour in the reactor. Other things important. Methane undergoes destruction is radiolytic destruction with CO2 to form carbon monoxide and again more water vapour. And finally, you're probably more familiar with the water-gas shift reaction, where the equilibrium between the carbon monoxide and steam giving CO2 and hydrogen. So you can see that there's several issues here. Apart from the graphite mass loss, there's the steam production, which is not good at high temperature on steels. And there's carbon monoxide production and hydrogen production. Now, hydrogen isn't actually controlled in the reactor. You get what you get in a situation, but you do control the other species. We put about 240 parts per billion of methane in. Carbon monoxide is injected into the reactor at about 1%, and that's really to shift this reaction the other way, to slow down, if you like, the oxidation of the graphite. So on the next slide rather, we've mentioned the graphite weight loss. We mentioned steel oxidation because of the water vapour production. Deposition is an issue, and that's brought about because of the carbon monoxide and also the intermediates that are formed. For example, ethylene, or ethene as I should call it, leads to carbon deposition depositing on fuel and boiler surfaces, and that inhibits heat transfer. To mitigate that, we add carbon sulfide, and I'm going to talk a bit about that later. But just to give you a feel for the sort of levels we're talking about, with 1% here, 260 for the methane. Water's controlled using dryers in a bypass plant, and again I'll show you that in a moment. And the carbon sulfide is added to mitigate carbon deposition. So the bypass plant, there's a small bleed from the reactor. I mentioned 4 tons a second circulating. I think this is something like 20 kilos a second, so it's a fairly small flow, and it's filtered and put through a recombination unit. The recombination unit is basically a platinum catalyst on alumina, and it's there to remove any excess carbon monoxide that's formed. I mentioned earlier the continuous formation of carbon monoxide, and obviously oxygen is needed to inject into the unit to form CO2. The water vapour, which is produced all the time, is controlled in the gas dryers, and this is a desiccant, and usually there's either 2 or 3 of these desiccant towers, depending on the reactor design, one in standby, one in operation, and one regenerating. You can regenerate them. They absorb water vapour at a relatively low temperature, and then to dry the water vapour off, once they become saturated, you heat them up and condense the water. And this is usually done on a time cycle. Incidentally, the water that comes off the dryers will be reasonably concentrated in tritium. So tritium is a main radioactive discharge here from the AGRs. A filter is put in at the back end of the dryers to prevent any desiccant fines, and here we have the methane injection for mopping up the oxidizing radicals, CO2 makeup if necessary, and then back to the reactor. So just to summarise the functions, we're trying to maintain a constant carbon monoxide concentration using the recombination unit. We're removing excess water using desiccants. We're injecting methane to mop up oxidizing free radicals, and then the other functions are CO2 supply to the reactor. And if we want to blow down the circuit or purge the reactor, we do that via the gas bypass plant as well. And I'm sorry about that. That's just sort of like an engineering diagram to show you what it's like. We've got the dryers here. We've got a I can't read what that says actually. I think there's a heat exchanger there. That's a recombination unit. That's right, and that's a filter. So it's quite a complicated system. I mentioned carbon deposition earlier, and the precursor for this is ethene. One of the mechanisms of carbon deposition is via nickel transport. In the reactor, you'll have several types of nickel alloy, and this will interact with the carbon monoxide to form nickel tetracarbonyl, and unfortunately nickel tetracarbonyl is volatile, so it gets into the gas phase, gets transported around the reactor, and in cooler parts it can deposit. Now the kinetics of this and the thermodynamics of this is such that to increase the temperature you'll increase the rate of formation of nickel carbonyl. But the thermodynamics in that sense is in your favour. An increase in temperature shifts the equilibrium the other way. So although at high temperatures you'll reach equilibrium faster, there won't be the concentration of nickel carbonyl won't be as much. And there's obviously a critical temperature. It's about 200 centigrade where you can maximise the nickel carbonyl concentration. So this leads to a problem on cooler surfaces. The nickel carbonyl decomposes and actually deposits nickel. And nickel is an effective catalyst for carbon deposition with the ethane precursor. So that's the mechanism as understood today. There are other types of carbon deposition processes. We've just talked about the catalytic deposits. There's also dust and debris from thermal expansion of deposits in the material surface, and also radiolytic deposits which are found in the fuel route. But the main concern is the in-reactor catalytic deposit. And this is where carbonyl sulfide comes into play. Carbonyl sulfide will act as a poison to any nickel catalyst that's deposited on the surface. We already have sulfur 35 in the circuit naturally, and it was found that reactors which had oil leaks, the gas circulator oil leaks, in other words there was a higher amount of sulfur in the circuit, were found to have less carbon deposition than the other reactors. And so at the moment we're adding about 100 parts per million to reactors like Hartlepool, for example, and the safety case is being made to increase that to about 200, parts per billion I should say, to 200 parts per billion. Unfortunately, you need quite high levels of COS to suppress the deposition at high temperatures. And one of the negative things about COS is the increased S35 discharges, which, although it's only a beta emitter, it's still of concern to the Environment Agency. I'm now going to move on to pressurised water reactors. And here we're looking at something that operates at about 160 bar primary temperature of 300 centigrade with a primary flow of about 20 tonnes a second. And on the steam side, you have a primary side and a secondary side. On the secondary side, that operates about 70 bar and 285 centigrade. So this is a totally different reactor. And here it is. I apologise for the gory colours on there. But Sizewell B, for example, will have 4 steam generators around the primary circuit, just one pressuriser. The steam separators giving high quality steam driving a turbine, condenser going back into the steam generator. But on the chemistry of this, on the primary side, instead of during a fuel cycle, instead of gradually pulling the control rods out to compensate for the fuel burn up, it's usually done with what we call a chemical shim, and that's boric acid. So boric acid is in fact dosed into the primary circuit, and as the fuel's burnt up, the boron's taken out through the cycle to compensate, and this saves moving control rods up and down all the time. That's fine, except B10, which is the nuclide, which is the neutron absorber. There's only about 19.6% B10 in natural boron. All the rest is B11. The B10 undergoes an alpha reaction, producing lithium-7. Furthermore, acid and water at high temperatures is not a good idea, so we have to adjust the pH. We do this with lithium hydroxide as we're producing lithium, so we're not really adding anything new into the circuit. Furthermore, it's lithium-7 hydroxide we add. Natural lithium, although there's a high percentage of lithium-7, there's also a small percentage of lithium-6. And that's potentially a problem because lithium-6 also undergoes an N-alpha reaction producing tritium. So if you don't take out the lithium-6 out of natural lithium, you end up with a reactor which is building tritium up to unacceptable proportions. So we use, I say enriched in lithium-7 or depleted in lithium-6, lithium, for the addition there. Now the criteria for the pH really depends on the solubility of the corrosion products. We're going to have a look at that at the moment. Early experiments were carried out on magnetite, looking at the solubility of magnetite as a function of pH and temperature. And I suppose let's just look at the next slide, and you can see it's certainly not a linear situation. This is temperature along here, and each one of these lines represents a different pH, and it's written in terms of micromoles of potassium hydroxide. That's how the experiment was done. So we've got ion concentration, and we're only interested in this region really, around between 280 and 330, because that's where we're operating in the core. If you imagine the inlet water in the core at about 285, as it goes through the core, it increases in temperature and comes out at about 290, 293, something like that. So you can see here, we've the slope of this line, it could be negative or positive depending on which pH you're operating. If you were to plot that the other way round, in other words, if we just take a series of temperatures now and plot the solubility against the pH, we can get a better picture of what's going on. Now the important thing is to mitigate against CRED deposition, in other words, corrosion product deposition. We need to make sure that the temperature coefficient of solubility is always positive. In other words, as the temperature of the water increases through the core, then the solubility of the corrosion products increase, and that will prevent to a large extent any deposition on the core. Deposition on the core is a bad thing because of the neutron flux producing cobalt-60, for example, which can then spool off and deposit itself around the circuit again. So we're looking for a pH operating in this region, and based on magnetite data, this is now a little bit historical, we find that the pH is about 6.9, and just bear in mind that pH at 6.9 is at 300 centigrade. Everything's measured relative to 300 centigrade because that's a sort of an average operating temperature. And so in the early operating day, well, not so early operating actually, on the early operating days they didn't bother with pH control and they ran into all sorts of problems. These were the old reactors in the States. But now, say at the beginning of the cycle, we might start somewhere here at 1200, 1100, and we'd coordinate this pH. So as we remove the boric acid to compensate for the reactivity in the reactor, we take out the lithium to follow the pH down. We have to take out the lithium because it's being produced all the time by the B10 N-alpha reaction. Nowadays, more recent data, everything's based on the solubility of nickel ferrite, which is a substituted magnetite. And here we find that the critical pH to maintain a positive temperature coefficient of solubility is 7.4. Now that could lead to a few problems, because it means at the beginning of a fill cycle you'll need to put in about 10 or so parts per million of lithium-7 to maintain that pH. And unfortunately the fuel is not guaranteed for that amount of lithium. The fuel manufacturers will specify an upper limit of about 3.5 parts per million maximum, or the guarantee of the fuel is invalid. And this is because of the zircaloy cladding on the fuel is corroded by lithium hydroxide. So what they do is put in as much lithium as they dare, and then when we reach the pH of 7.4, we just coordinate it for the rest of the fuel cycle. I'm just going back to remind myself, yes, okay. That's the pH criteria. Another very important aspect is redox. And here, if you've got water in a high radiation field, you're going to produce all sorts of free radicals, some of which are oxidizing, some of which are reducing. But overall, if you subject pure water to radiolysis, you'll give rise to an oxidizing situation. I don't know whether any of you are familiar with the radiochemistry. We use G values, which is the number of molecules produced per 100 electron volts absorbed, and we find that oxidizing species are about 2.8 and reducing at 2.7. Now, the oxidizing species, of course, are going to do a fair amount of damage to the steel in contact, or the metals and alloys in contact. So we mitigate that by dosing with hydrogen. And hydrogen will just mop up any excess oxygen that's there, but that's not its only function. If you look at this graph, you don't need that much hydrogen, in fact, to mop up the oxygen. It's the other free radicals that are doing the damage, the OH and the HO2. Here's the HO2. And we need quite a bit more hydrogen to bring that down to an acceptable level. So you'll find that plants will operate somewhere between 25 to 50 standard cc's per kilogram of hydrogen. I mentioned, before we talk about startup and shutdown, I mentioned the tritium in the lithium-6 aspect of the coolant. It's not possible to remove all the lithium-6 from your lithium you dose, so there'll invariably be some tritium produced. So when we shut down, we have to be absolutely certain that the tritium levels in the coolant are acceptable, because the vessel head comes off and it's going to expose the refueling guys to the water vapour. At startup, we'll do it in the order on there. At startup, you're taking a cold oxidising coolant up to a hot reducing coolant. And apart from the usual vacuum deaeration vacuum techniques, we use hydrazine to actually dose at startup, because that's an oxygen scavenger, and you produce nitrogen and water, which are quite acceptable. At shutdown, you're wanting to take a reactor which is under hot reducing conditions down to cold oxidizing conditions, ultimately you're going to expose the whole thing to air to get the fuel out for refueling. You can do it with air, but it's expedient to do it with a hydrogen peroxide. It's a controlled oxidation process. It's rapid. It saves time. So this is what happens. Unfortunately, when you go into oxidizing conditions, all the transition metals, which were normally in the +2 oxidation state, go over to the +3 oxidation state, and they will dissolve. They will become soluble, and furthermore, you have particles spalling off the surfaces. So this effect during shutdown is called a crud burst, and you get a massive peak, several orders of magnitude increase in corrosion product activity in the coolant. This is not a problem. It's taken out in the chemistry, in the chemical volume control system. And again, sorry for the complication about this. Basically, you've got a heat exchanger. This operates at about 45 centigrade, so it's near ambient temperature. So you have a heat exchanger to bring it down. You've got some ion exchange resins here. These control taking out the soluble crud, the ions, cobalts, any fission products. You've got a mixed bed there, things like iodine, and you've got a cation bed. Now the cation bed is purely there to control the lithium. You're producing lithium from the B10N alpha reaction all the time. It has to be taken out on the cation bed. The volume control tank is there to maintain firstly to maintain the hydrogen concentration. That operates with a hydrogen overpressure there, about 2 bar. And also, because it's flushed out with hydrogen all the time, you're taking out all the fission gases, all the xenons and kryptons, and that goes off to the gas waste reprocessing plant. You also have a filter as well in here for particulates. So then the main features of how you control are, I should mention the chemical dosing tank. You put your lithium hydroxide and hydrazine, hydrogen peroxide in the chemical addition tank. So as I say, we're operating about 45 centigrade. Cation resin for lithium control, removes cesium, which is a fission product, anion resin for iodine removal, and also the non-active impurities. For example, you keep the sodium and the chloride levels down. There's a mixed bed in operating the borate form that will remove those. And I've mentioned the chemical addition tank, volume control tank. The size will be, this operates at these sort of temperatures and pressures. The Westinghouse AP1000 has an interesting feature that it has an in-containment chemical volume control system that's actually operated at pressure. So there's a slight design difference there. I've mentioned zinc addition. Zinc's a D-block metal, and it can replace nickel and cobalt in the oxides on surfaces, which means, of course, that it minimises their release later on, or actually minimises their absorption and formation. And so there's been a big debate about zinc addition in pressurised water reactors, and quite a lot of plants have adopted this with success, both old plants and new plants. We'll have a look at boiling water reactors now, and I've put both types up there just as a comparison, because the important feature, the boiling water reactor, doesn't have a primary and secondary side. It's just one big kettle, if you like. You're boiling water, and you have a steam separator, and it goes straight into the turbine, and it drives the turbine. So that in itself is an interesting situation, because the whole emphasis on BWRs is the prevention of stress corrosion cracking. if you've got components in there under tensile stress, there's a potential for chloride-induced stress corrosion cracking because of the inbuilt tension in the component. That's the ionic impurities. There's radiation effects. We're going to talk about a bit of hydrogen addition and a process called noble metal chemical addition. And then if we've got time, on a bit on fuel integrity and flow accelerated corrosion on that. But the background to this, back in the 1970s, stress corrosion cracking in stainless was always recognised as a problem. And annealed 304 was developed stress corrosion cracking in heat affected zones, and also it was seen in nickel alloys, and it was due to either impurities in crevices or sometimes cold working during fabrication and the radiation induced cracking. And the water impurities, of course, chloride in particular, initiates crack growth. And so the two water chemistries were developed. But the early one was normal water chemistry, and basically this is just pure water with nothing added to it. So you've got your impurities in there, and you're in oxidizing conditions because the radiolytic field produces oxidizing free radicals, and it was found that chromates in fact were the major contributor to conductivity because of the chromium in the materials in contact. The chromate was about 25 parts per billion. Zinc additions were done here. Now obviously to change from oxidizing conditions to reducing conditions, you can add hydrogen. So later on this was done to maintain reducing conditions. Nitrates and chromates were reduced, and the zinc levels were maintained, and these were found to reduce the crack growth. Flow rate effects were important. In fact, if you increase the flow in a region, bearing in mind that we're not just talking about the main vessel, we're talking about all different parts of the vessel and components, you get a reduction in boundary layer with increased flow, which means an increased flux of oxidizing species, and this results in an increase in the electrochemical potential. But convection dominates over ion migration diffusion, and so although the flushing of a crack tip is beneficial, the convective flow subsides as you disappear into a crack. Temperature effects. I know this looks a bit like a sky at night, but there is a sort of slight correlation there. And for high purity water, we found a maximum crack growth at about 200 centigrade, and the crack growth decreases rapidly above 200. But there's two competing effects here. There's a kinetic effect, which gives you an increase with temperature, but the electrochemical potential decreases with temperature. So if we look at comparison with, say, normal water chemistry and hydrogen water chemistry, the ECP here was quite high, and there's the driving force for stress corrosion cracking. So invariably for aging plants, we see an increased frequency of SCC. With here, we're down to minus 230 millivolts, which is the sort of the optimum range with the addition of hydrogen. And we've seen mitigation of stress corrosion cracking, reduction of oxidizing species. And it's interesting, although we talk about hydrogen water chemistry, we can have various types of hydrogen water chemistry, low, moderate and high. And various plants have adopted all of these regimes. You can see going from 0.4 up to 2 parts per million. We're going to talk a bit about noble metal chemical addition. This is, at the moment, it's dosed at shutdown to give a layer of a palladium or rhodium catalyst on a surface, and that's to encourage the hydrogen peroxide reaction. We add hydrogen to reduce the oxidizing species, but although it is a fairly rapid reaction, relatively speaking, in terms of the time scale of the core itself and the residence time, it is quite slow. So by adding a catalyst, rhodium or platinum, you can actually speed up that process, and in effect you can operate with less hydrogen. This slide is just an example of different hydrogen rates required for different parts of the reactor. It shows it's not a straightforward problem. Different parts of the reactor require different amounts of hydrogen to maintain an ECP of minus 230 millivolts. And here we see the effect of noble metal protection here. We did with the high hydrogen, moderate, low hydrogen, noble metal protection. It's usually this sodium rhodium nitrite complex or a platinum hydroxy complex that's added on the surfaces. At the moment it's done on a batch process, but there's a move towards continuous addition now of noble metals. Nitrogen 16 is an interesting issue. Nitrogen 16's always produced from the O16NP reaction, and that happens in the PWR as well. In a PWR, of course, it's restricted to the primary circuit, but in the BWR, you haven't got this restriction, so potentially could be carried over. So we add hydrogen to the feed water, and to produce more reducing conditions. So instead of nitrates, you might get ammonia produced. And then other volatile forms of nitrogen might be more important than ammonia, but unfortunately ammonia and O2 are both volatile, so really you're caught between two aspects here. So invariably local shielding of turbine components is required for dose management. Cobalt 60 is really an issue for both types of water reactor, activated from cobalt 59, which is always an impurity in steels. And the main contributors in BWRs are the soluble concentration in the water. And because the water's of a more oxidizing nature, if you like, than a PWR, you're going to increase the solubility. You can mitigate that with zinc and cycling between oxidizing and reducing conditions. So it's found that the effect of reducing conditions and adding zinc will reduce your cobalt 60 by an order of magnitude. So this really gives a summary of the dose management. Injection of hydrogen, operation with feed water, hydrogen, controlling the shutdown dose rate effects, avoiding increased steam operating dose effects, for example using noble metal addition, using zinc to control the cobalt 60 in films, and controlling feed water ion. I'm going to quickly go through these slides because we are running out of time slightly. Flow-assisted corrosion is another aspect. And again, we're looking at hydrogen water chemistry, reducing the amount of oxygen in the steam. But that potentially could increase the flow-assisted corrosion rates, because unfortunately you have an inverse relationship between the rate of flow-assisted corrosion and the concentration of dissolved oxygen. However, the use of noble metal addition didn't have any adverse effect on flow assisted corrosion in practice. And we've got plants with low hydrogen water chemistry resulting in higher oxygens. We've got low, comparing low and moderate hydrogen water plants there, at least an order of magnitude difference in the oxygen, hence the suppression of radiolysis and higher O2 in the steam. So on the next slide, there's fuel integrity concerns. Here we don't have the lithium issue, but we do have other corrosion aspects. A phenomenon called nodular corrosion it's seen on BWRs in oxidising environments. The oxide layer tends to be Fe2O3 rather than the magnetite, and the various impurities, for example zinc, copper from if you have copper alloy condensers, silica, zinc silicate, silica from the water impurity, and chrome from the steels. So for hydrogen, water and zinc, we limit hydrogen to 2 parts per million. We have zinc in there between 5 and 10 in the reactor water and 0.6 in the feed water. A few plants are in that situation. But here, with noble metal addition, that's applied during shutdown rather than start-up. We've got surface sporulation and thick tenacious deposits, and formation of thick tenacious crud is related to the high water, iron and zinc. That's just the strategy. I'm going to skip that and just summarise the plant chemistry. As you probably gathered, it's more of an art, balancing the chemistry on a BWR. So to summarise, we have normal water chemistry. You've got oxidising conditions, an increased tendency for stress corrosion cracking. Now we're looking to try and keep our chemistry down to minus 230 millivolts for the ECP. And so we do use hydrogen addition, but plants on moderate hydrogen addition show an increase in nitrogen 16 in the steam, and that's because of the ammonia coming off. And so to reduce this, some plants can batch dose with noble metals, which I've just mentioned, and that acts as a catalysis for the hydrogen peroxide and other oxidising species with the hydrogen. So we can mitigate stress corrosion cracking, and generally speaking, I think this is an accepted method of modern BWR operation. As I mentioned earlier, they're now thinking about continuous addition processes. So, in conclusion, our operating fleet, 7 AGRs, 1 PWR, we've got 1 Magnox left, with potential new builds, both the EPR 1600 and the AP 1000, and an advanced boiling water reactor. I've tried to do a few chemistry issues, overviews there. I'd like to thank you for coming along and listening, and happy and we'll try and answer any questions.